Okay, hi, now welcome to the first video on waves. Now in this video we're going to speak about the nature of waves and the different types of wave that you can get. But the first question really is, what is a wave? Well, a wave is basically a mode of energy transfer. So a wave is basically a way in which energy can move from one place to another. Now, waves can be broken down in categories depending on a few things. Now, two types of wave I want to speak about are firstly a mechanical wave and a electromagnetic wave. Okay, so what are these? Now, a mechanical wave is basically one in which vibrations are a way in which energy moves. So the vibrations require a medium in order to transfer the energy. Okay, now that might sound a bit weird, but basically all a medium is a substance. So this means that the waves have to travel through something. For example, a water wave is a mechanical wave because obviously water is the medium. Sound is also a mechanical wave, and normally air is the medium. Water can be a medium for sound, but air is the normal one, of course. Now, the other type of wave is an electromagnetic wave. Electromagnetic. And that should ring a bell because we spoke about that at the start of the course. Electromagnetic waves include things like infrared radiation, visible light, gamma rays, X-rays, radio waves, etc. Now, they do not require a medium. So, do not require a medium. So an electromagnetic wave can actually travel through a vacuum. The reason we can't hear explosions going off in space, because that would probably deafen all of us and kill us, is because there are vacuums in the way, and that means there is no medium to carry the sound. Sound is a mechanical wave, and so it needs a medium. However, light can reach us from the sun because it is an electromagnetic wave. It does not need a medium, and it will travel through a vacuum. And that is the difference between the two. Okay, so these two distinctions tell you about how the waves travel. Now, there are two more groups of waves, and they are not separate from these, but it's a different way of classifying them. And these are transverse waves, and longitudinal waves. Okay, so transverse and longitudinal. Now, what this tells us is about how the wave moves. Not what it moves through, but how it moves in terms of direction. Now, I'm going to use water waves as an example to start with. Water waves are transverse. Now, let's say you had a pond that looked like that, and it was all flat, and there's nothing really going on. And let's just place a seagull beautifully drawn like this, sitting on the pond. So like that, it's not actually sitting above water, it's not some kind of Jesus seagull, but there we go. So the seagull is just sitting there. Now, if we then made some kind of wave occur on this pond, so let's say that there was a wave machine on one side and we turned it on, then the pond would start to look a bit like this. Okay, so blah, blah, blah. These are obviously the waves. And where's Mr. Seagull? Well, he's sitting on top of one of these waves. Now, what's going to happen is the waves are moving this way. So the waves are obviously moving in a direction. However, what's going to happen to Mr. Seagull as the waves move? Well, when this wave drops down, he's going to drop down. And then when another wave comes, he'll be lifted back up, and he'll drop down, and he'll be lifted back up. But why isn't he carried along with the wave all the way to the shore? Well, that's because what's happening is, let's say, for example, this here is a molecule of water. Even though the waves are moving from left to right in this direction, the molecules of water are actually moving, let's try and get that, up and down like that. And so what we have is a scenario where the direction of the vibration will be the movement of this water molecule, and then in turn, obviously, Mr. Seagull, the direction of the vibrations are at a right angle to the direction of movement of the wave. So, seagull moving up and down, but the wave moving forwards. Now that defines a transverse wave. So the direction of vibration is perpendicular to the direction of movement of the wave. Okay, now opposite to this is a longitudinal wave. And a good example of a longitudinal wave is a slinky. If you've ever played with a slinky before, then you've seen a longitudinal wave in action. So what's happening is the wave is moving this way because these are seen as waves, and this here, where everything is bunched together, that will move forwards and backwards like that. And so it looks quite cool, especially when it's all different colours, but it moves back and forwards, and that is the wave. But what's actually happening in terms of vibrations? Well, each one of these lines is actually a rung of the slinky, if you like. It's one of the coils. And these are moving back and forwards into each other. So the direction of vibration is also back and forward. So vibration is back and forward. So therefore, the vibration is parallel to the movement of the wave. And the movement of the wave tells us the movement of energy. So the wave moving is energy moving. Same with up here. Okay, so that's the difference between a longitudinal and a transverse wave. There are various different examples. A slinky is of course longitudinal. Sound is also longitudinal. And so I'll just demonstrate that quickly with a diagram. Let's say we had a speaker over here, okay? And that booms out some sound. What's happening in the air is you've got all these air particles, right? And basically, some of these are going to be pushed into the others. And let's say we took a snapshot. Some of the air is going to be in a bunch because they're just about to push each other away, whereas other air particles have pushed each other away already, and they're moving to the next bunch. So there's going to be another bunch of air particles which are all close together, and eventually they will move away. But after those, there are also air particles which have moved away. And so what we've got are these bunches and then spaces where everything is far apart. And we have terminology for those. And this is only in longitudinal waves. So these things here, which are the same as these here, when everything is close together, are known as compressions. So you know that when something is compressed, it means pushed close together, and that's exactly what we see here. Now when things are far apart, as we can see here, and we can see here, this is known as a rarefaction. Strange word. Rare as in R-A-R-E, rarefaction. And this is where everything is far apart. Okay, so there's more terminology that we're going to go on to in the next video, but I wanted to make sure that you know what these terms are straight away. Okay, now the last point I want to make is that longitudinal and transverse waves are not separate from electromagnetic and mechanical waves. Now a transverse wave, both mechanical, let's do this in a different colour. So here we go. Let's do it in blue. So both mechanical and electromagnetic waves can be transverse. In fact, electromagnetic waves are always transverse. Okay, you can't have a longitudinal electromagnetic wave. However, mechanical waves obviously can also be longitudinal. So sound is a mechanical wave and that is longitudinal. A water wave is also mechanical, but that is transverse. But all the electromagnetic waves, so gamma rays, X-rays, visible light, infrared, etc., all of them travel in the same way, and that is transverse. They all don't require a medium. They all travel at exactly the same speed. So the speed of light is actually exactly the same as the speed of UV, the speed of infrared, the speed of gamma rays, radio waves, etc. All of those waves travel at exactly the same speed. Okay, so that's quite a lot of information, so I'm going to stop there. If you have any questions on that, please do comment in the box below or send me an email directly using the link, and I'll be sure to get back to you. But I look forward to seeing you in the next video.